So when we talked about hydride reactions in the previous screencast, um, and what we saw was that an acid derivative could be reduced using a hydride to a primary alcohol, and that goes through an aldehyde intermediate. And so what that means is once that aldehyde's formed, it quickly reacts with a second a second reduction with the hydride. But in some situations, it's advantageous to stop at the aldehyde. And so there are two specialized reducing agents that are commonly used for this purpose. One is lithium triterbutoxy aluminum hydride, which is Ltba, and the other one is diisobutyl aluminum hydride. And I want to go ahead and give you kind of a heads up. I've done this reaction before. Also, it had an older name or older abbreviation, which was dibol, like that. And so a lot of times it's hard. I'm old, and it's hard for me to switch from dibol to diba. But I'm trying. So particularly because I did this reaction for a while. So a few things to point out with these kind of specialized reagents. Both of these compounds possess an aluminum hydrogen bond, and are hydride sources, much like a lithium aluminum hydride. And you can, of course, see the structures written out here. Okay, so these are these are hydride sources. And so when you see these written in equations, you will either see the abbreviations used, or you will see it written out like that. So you can see either of these things, and like I mentioned before, in some older text, you're going to see dibol as it written out. So let's some examples of how these are used. Lithium terbutoxy aluminum hydride, Ltba, is commonly used to reduce acid chlorides or acyl chlorides to an aldehyde. Right? And this happens at low temperature. And then dibol is commonly used to reduce an ester to an aldehyde at low temperature. And so when we think about this, it's helpful to look at the mechanisms. And see where they stop. So we're going to look at the mechanism for Ltba. And we're going to start by drawing the reactants. Right? And then we have a nucleophilic addition reaction where we have a hydride donor here, and it's going to work like everything else we've seen, right? We're going to attack that carbonyl-carbon because it's partially positive, and the electrons are going to go up onto the oxygen, and we've made a tetrahedral intermediate. Okay, and now with this tetrahedral intermediate, it's going to undergo a tetrahedral collapse, and we're going to have a nucleophile elimination. So these electrons are going to go down here, and these electrons are going to go there. Now, here's the deal. The reaction stops here, okay? And the reason is because the second addition of H minus, not from H minus, of H minus right, from from Ltba is much slower than the first, right? So once the reductions come to completion, the reaction can be stopped, right? And so there are two reasons why the reduction with lithium triterbutyl aluminum hydroxide is significantly slower than the reduction of lithium aluminum hydride. And one of this is the bulkiness of the tert butoxy groups, right? And so that really introduces some significant steric hindrance in the nucleophilic addition step. And then two, the reaction is carried out at really cold temperatures. About negative 75 degrees Celsius, right? And so, colder temperatures, according to molecular theory, right, is molecules move more when they are warmer, and so that if we increase the temperature, their reactivity increases. So by cooling this down, the molecules move slower. At room temperature, right, the lithium tert butoxy aluminum hydride reduction is not controlled, so the acid chloride is reduced twice all the way down to the alcohol. So if you're at room temperature, it will reduce to the alcohol. So that lower temperature is very helpful. Now, the reduction of an ester by eyeball also stops at the aldehyde stage, not because the second reduction is slower than the first, but because the tetrahedral intermediate that's formed is relatively stable at very cold temperatures. And so let's look at that mechanism. Oh, and I didn't leave myself enough room to draw the aluminum. So hold on. Al. And let me make the second group kind of go back here, because that's a big old molecule. All right. There we go. So we got these two guys. And the first thing we're going to do is a nucleophilic addition, right? Where these electrons come in here, right? And those electrons go there. Okay. And so I'm just looking back and forth, I'm double checking my carbons and my heteroatoms and just making sure I have all the bonds. So I followed the arrows, and now and then I'm always double checking, always looking back and forth, always double checking. So make sure you're doing that as well. Now, this tetrahedral intermediate is stable at negative 78 degrees and will remain stable until, sorry, there's no stereochemistry there. Those bonds are just bothering me. And will remain stable until the acid is added for the acid workup. And acid workups are kind of fun. You just add the acid and you wait. So it's H3O plus. And what we end up with here is that this is now an alcohol. and then we have an H there. Okay, and what we're going to see here is any excess water converts the hemiacetal into the aldehyde. Okay, so we've got some excess water running around, and now right. So in the diball reduction of an ester, the aldehyde product and the reducing agent are not present in the mixture at the same time. So the aldehyde and reducing agent are not present at the same time. So the aldehyde can't be further reduced to an alcohol. Now, the relative stability of the tetrahedral intermediate in the diball reaction here can be rationalized in part with chargeability. So what we see here is that the elimination of an alkoxy leaving group from the tetrahedral intermediate would generate two additional charges, a negative charge on the oxygen atom of the leaving group and a positive charge on the oxygen atom bonded to the aluminum. And so the small size of the oxygen does very little to stabilize those charges. So the uncharged tetrahedral intermediate is just more stable, right? It's just going to hang around. And so until, of course, we do the acid workup. Now, like hydride anions, alkyl anions, can act as nucleophiles, but not leaving groups. So when we talk about this, right, an alkyl anion is an R-, okay? So sources of alkyl anions are organometallic compounds like alkyl lithium reagents, which we've messed with before, Grignard reagents, right, where X is a halogen, and then lithium dialkyl Cooperits, which I always have a hard time saying, okay? Now, as with hydride reagents, the products of a nucleophilic addition elimination reaction involving one of these organometallic reagents is not an acid derivative. And so we can see this when we look at the reactions shown here in equation 2233 and 2234, where we have an acid derivative. It's treated with alkyl lithium, shown here, and a Grignard reagent shown here. And what we see is that two equivalents of the R- groups have been added. And then, of course, we end up with an alcohol where our carbonyl carbon was. So, in general, what we find is that acid chlorides, acid anhydrides, and esters can be treated with alkyl lithium or a Grignard reagent to produce a tertiary alcohol. Okay, and so in each of these cases, one of the things to be aware of is that two equivalents of the R- nucleophile have to add to produce that tertiary alcohol. I also want to point out that ether is generally the solvent here, because if there's any water, it will cause both of those reagents to be unreactive. And so there's also an acid workup step that for the final step of the reaction. But those are sequential, so they're done with timing. So generally, when I've done this one, for example, we would add these together. They would mix overnight, so a reflux for 18 hours, depending on what temperature the reaction called for. And then you'd come in the next morning and you would add the acid in the water and then do the acid workup. And so that's generally how that works. So let's look at the mechanism for the Grignard reagent. Okay, we're starting with our acyl chloride, and we are, from our Grignard reagent, we are going to go ahead and just show the alkyl group, which is right here, okay? And it's going to undergo a nucleophilic addition, where these electrons are going to come in and attack that, and those electrons are going to go up there. Okay, and so I'm looking back and forth and I'm drawing my product. And I see that when I follow my arrows, I have a tetrahedral intermediate. And now this is going to go through a tetrahedral collapse in a nucleophile elimination. Okay, where these electrons are going to come down here, right? And they are going to bump off this chlorine. Now we end up with a double bond and a CH2, CH3 plus the Cl minus there. And what can happen here is that a second equivalent of the CH2, CH3 in a nucleophilic addition reaction can be added. And so it comes in, it adds here, and those electrons go there. And now we have this, and we are, and so that's all done like under nitrogen. The reaction flask or round bottom flask is, if it's refluxed, it's under nitrogen, and otherwise it's got a septa. It's got a septa on the flask, right? So because we don't want to introduce any oxygen, we don't want to introduce any water. Even water from the atmosphere will deactivate this reaction. So you let this run overnight, you come in the next day, you do an acid workup, and so you're going to add that H plus from all that acid running around in a proton transfer reaction. And now we have a tertiary alcohol. Now, all those similar mechanisms can be drawn with carboxylic acids or amides. These reactions are generally avoided. Amides are significantly less reactive than esters, and carboxylic acids are acidic, so they just protonate the R- nucleophile in a side acid-base reaction that we're not really interested in. Now, let's talk about the dialkyl Cooperit reaction. Sorry, I skipped ahead there. So if that broke up, that's what was going on. All right, so if there was a lot of breaking up there, I had to pause for a second, and so now I'm on the right slide. All is well. Okay, So it can be advantageous to carry out reactions where only one equivalent of R minus adds to an acid derivative. And so that means we would have a ketone that can be isolated. And one way to carry this out is to use lithium dialkyl cuprates, which are shown here. An acid chloride can generally be treated with lithium dialkyl to produce a ketone. And as we learned way back in chapter 18, the mechanism involved is different from the mechanism with a Grignard or alkyl lithium reagent because of the nucleophilic character at the copper atom. So anyway, we can think of this R2 CuLi as a weak source of R minus that tends not to react with ketones or aldehydes by direct addition. So the R minus will add to the C double bond O group of an acid chloride though, which is much more reactive than the ketone or aldehyde. So this is color coded and we can see where it adds right here, okay? Now, under these conditions, this ketone doesn't react any further. Lithium dialkyl cuprets also do not react with esters or amides, which are significantly more stable than acid chlorides. So to convert an ester or amide into a ketone, we need to convert it into an acid chloride. So we'll talk about that later, but right now I want us to do a problem. So we're going to show how to carry out this synthesis. So what precursor can be used to produce the alpha beta unsaturated ketone would be the first question that I would ask. So we are trying to, so when we look at this, right, I want to point out there's an alpha beta unsaturated ketone, and that's what we are trying to produce. And we remember that these can be produced from an aldol condensation. Right? And so then we need to ask ourselves, right, once we undo an aldyl condensation, right, where we look here and we undo an aldol condensation, which when we undo that, remember we cut right through there, okay? And so, and it would ring open. Right? This is still not our precursor, okay? So when we look back up here, we've got a chlorine here, but we have a CH3 here. And so the question would be, well, how can we substitute a chlorine for the CH3? And so to do that, we would undo an acyl substitution, right? So acyl chlorides are really reactive. We're starting at the top of the ladder. That's exciting, right? And so we can put an acyl substitution with an aldol condensation. Now, and so I kind of answered that question, the second question there. So now the question we need to ask ourselves is, what reagent should you use to carry out a single addition of the R minus to the acid chloride? And that's going to be that copper lithium. And so when we look at this, going in the forward direction, right? The copper lithium is what we're going to use. And then for an aldol, remember, we use sodium hydroxide and H2SO4 and heat. And that is how we end up with our alpha beta unsaturated ketone, just like that. So this for us ends chapter 22. We will continue to look at reactions that build off of this in chapter 23. As always, feel free to stop by my office if you have questions.